Hello, I'm Fleshed Out Thoughts, and I love fleshing out thoughts for extended periods of time. I'm building a full stack e-commerce platform for digital products and software services with Next.js and Supabase. This series is about the architectural decisions behind the platform, what I built, why I built it that way, and what I do differently. Today, we're going to be getting into state machines for my e-commerce platform, how I model order life cycles, payments, and coupons. Without further ado, let's jump right in. There's a category of bug that only appears when two things happen at exactly the same time. A user clicks cancel order while a Stripe webhook is confirming payment. Two customers both apply the last use of a limited coupon. A payment retries arrives after the order has already been refunded. These bugs are hard to reproduce in development because they require concurrency. They're hard to catch in code review because nothing looks wrong. Each operation is valid on its own. And they're catastrophic in production because they corrupt business state in ways that they are almost impossible to unwind. Here's why they happen. Every one of these bugs occur because the valid operations on an entity depend on what state is currently in, and nothing in the code explicitly tracks or enforces that dependency. Can this order be canceled? Depends entirely on its current status. When that dependency is implicit, scattered across if statements, Boolean flags, application conventions, concurrent operations can both have checks that should have been mutually exclusive. State machines make that dependency explicit and enforceable. Define your states, define which transitions between them are legal, put guards on those transitions, enforce them at the database level so concurrent operations can't sneak past checks that application code alone can't atomically protect. State versus data. Before the machines, I needed to draw a distinction that took me too long to learn. State is not data. Data is what an entity holds: an order's total amount, the customer's email, the product name. State is what governs behavior. Which operations are currently legal? An order's status is state. Changing it changes what you're allowed to do next. You can cancel a pending order. You cannot cancel a completed one. The test is simple. Does changing this field alter which operations are permitted? If yes, it's state. Model it explicitly. If no, it's data. The most common anti-pattern is storing state as multiple Boolean flags. Is paid, is shipped, is canceled. 3 Booleans create 2 to the third combinations, right? But your business logic probably only treats 3 or 4 as valid. The remaining 4 or 5 are impossible states. Contradictions like is shipped true, is canceled true, that can never legitimately occur, but that your database will happily store if any code path produces them. The impossible combinations are representable in your schema. Type checking doesn't catch them. Your database doesn't catch them. The only protection is the correctness of every code path forever. Replace those 3 Booleans with a single status: enum, draft, pending payment, paid, shipped, canceled, 1 variable, and legal values. Impossible states become structurally impossible, not just conventionally avoided. The order state machine. Here's the state machine that runs my checkout flow. The order starts at draft. When the user submits, it moves to pending payment. If payment succeeds via a Stripe webhook, it moves to paid. From paid, it can move to fulfillment in progress, then to completed. That's the happy path. The side transitions are where the machine does its real work. From pending payment canceled, if the user cancels before paying or payment fails. If Stripe declines, right? From paid to refunded. From fulfillment in progress to canceled. If stock runs out, but in the case of digital products, we don't worry about that. From completed to refunded within the return window. The terminal states: completed, canceled, refunded, payment failed, shown as double circles. This isn't just a diagram convention. Terminal states are an active protection against state machine resurrection. A late arriving Stripe webhook cannot repay a refunded order because there's no transition defined from refunded to paid. Without explicitly defined terminal states, a webhook that arrives 30 seconds late after a refund can bring a closed order back to life. Quick note on payments, right? My order state machine doesn't own the payment lifecycle. Stripe does. Stripe's payment intent has its own state machine. Requires payment method, processing, succeeded, cancel. My machine reacts to Stripe's state change. When Stripe says payment intent succeeded, my machine transition. My machine is a subscriber to Stripe's machine, not a replacement for it. So transitions with guards. Why atomicity matters. Every transition has a guard, a condition that must be true for the transition to fire. The transition from pending payment to paid has a guard. The payment amount must be greater or equal to the order total. If Stripe sends a webhook for a partial payment, the transition is rejected. The transition from fulfillment in progress to completed requires a tracking number. You can't complete an order without shipping it. The transition from completed to refunded requires the refund to fall within the return window. So why does it matter that these guards live in the database rather than the application code? The atomicity. Here's the failure mode for application level guards. Your code reads the current state, evaluates the guard, decides that the transition is valid, then writes the new state. Between the guard check and the write, another concurrent transition can modify the same row. Your guard passed, but against a state that no longer exists. When the guard and the state update live in the same database function call, protected by a row lock, there is no gap between check and write. The guard is evaluated and the state is updated as a single indivisible operation. No concurrent transaction can modify the row in the window because there is no window. That's what evaluated atomically means. Not just fast, but physically impossible to interleave. So concurrent transitions. The hardest state machine problem is concurrency. A Stripe webhook confirms payment. Simultaneously, the user clicks cancel order. Both see the order in pending payment. Both try to transition it. One to paid, one to cancel. What happens? My transition order status function uses select for update. It requires a row lock on the order for the duration of the transaction. The first event to arrive, the payment webhook, gets the lock, reads pending payment, validates the transition, updates to paid, and commits. The lock is released. The second event, the cancellation, arrives a millisecond later and blocks on the lock. When it acquires the lock, it reads paid. The transition paid moves to canceled, is not in the transition table. The function returns an error. One transaction wins, the other loses cleanly. No corrupted state, no partial updates. The last mile matters. The cancellation server action receives that error and must do something useful with it. The right behavior is to return a response that tells the client your order was paid before the cancellation could be processed and prompt the UI to refresh, right? The state machine returns the right answer. The application surfaces it. Idempotency. Safe webhook handling. Stripe delivers webhooks with at least one semantics. The same payment intent succeeded event can arrive twice. This is not a bug. It's a deliberate design decision. Guaranteeing exactly once delivery across a distributed system with unreliable networks is probably impossible. A message is sent, the recipient processes it, the acknowledgement gets lost in transit, and the sender resends. Stripe, Kafka, SQS, PubSub, all of them guarantee at least once. Idempotency is the receiver's responsibility. This is the industry standard model. My solution, every Stripe event carries a unique event ID. My order events table has a unique constraint on that ID. When a webhook arrives, the handler attempts to insert a row with that event ID inside the same transaction as the state update. Here's a concurrent delivery path worth tracing precisely. 2 webhook deliveries arrive simultaneously. Both start transactions. Both query for the event ID. Both find nothing because neither has committed yet. Both application level checks pass. Both attempt to insert. The unique constraint is a database level constraint. Only one insert can succeed. The second fails with a unique constraint violation at the database level, not the application level. That's the atomicity that makes this safe. The database enforces uniqueness, not application code that could have a race of its own. Move on to database level enforcement. Application level state machines can be bypassed. A direct SQL update in a migration script, a manual fix during a production incident, a batch job that updates rows without going through the server action. Any of these can put an order into an impossible state if the only enforcement is in application code. So I enforce at the database level too. My orders table has a check constraint ensuring the status column only contains valid enum values. But a check constraint alone allows jumping from draft directly to completed. It validates the destination, not the transition. So I have a trigger that fires before any update on orders. The trigger looks up the allowed transition for the current status and rejects the update if the new status isn't in the allowed list. Even a raw SQL query can't put an order into an illegal state. The trade-off worth naming: triggers introduce coupling. If I add a new valid status, I need to update both the application code and the trigger. The migration: store the valid transition map in a database table that both the trigger and the application function read from. One source of truth to update when the machine changes. Coupon usage: a microstate machine. The same principles apply to resources that aren't full entities. The coupon system is a perfect example of a general check then act pattern, the source of most concurrency bugs in web applications. The pattern: read a value, make a decision based on it, write something back. If another concurrent process can modify that value between your read and your write, you have a race condition. A coupon has max uses, say 100, and a usage count. Two customers simultaneously read, usage count is at 99. Both check. Is 99 less than 100? Yes. Both increment. The result is 101 uses of that 100 use coupon. My increment coupon usage if valid function uses select for update to lock the coupon row. The first checkout acquires the lock, reads 99, passes the guard, increments to 100, commits. The second blocks, acquires the lock, reads 100, fails the guard because 100 is not less than 100, and it returns an error. No 101st use. This is a state machine in microcosm. Two states. My transition logic is a function mapping current state to new state and guard result. For a machine with 10 states and 20 transitions, that's clearer than any abstraction. Upgrade when you have over 50 states and complex guard dependencies. No event sourcing. States stored directly on the order row. Order events gives an audit trail, but nothing is reconstructed from it. Upgrade when you need to rebuild state at any arbitrary point in history for compliance, analytics, or time travel debugging. No sagas or workflow engine. Checkout is one server action in one database transaction. Upgrade when checkout spans multiple independent services that can each fail dependently. No scheduled timeout processing yet. Auto-canceling abandons drafts after 24 hours is on the roadmap. The transition slots are already reserved in the FSM. Upgrade to a workflow engine when scheduling, retries, and timeout logic in one place becomes simpler than a cron job. Each of these simplifications would be wrong at a larger scale, but for a solo developer with a single database, simplicity is more valuable than architectural purity. The transitions are explicit, concurrent operations are safe, impossible states are unrepresentable. That's what matters. Testing state machines. State machines are unusually testable because the valid transitions are explicitly defined. The test suite writes itself from the transition table. For every state and event pair that should succeed, write a positive test. For every pair not in the table, write a negative test verifying the function returns an error. For every terminal state, verify rejects all events, including events that were valid in earlier states. Test the concurrent scenario. Two transactions attempting the same transition simultaneously. Run them with promise that all and assert exactly one succeeds and one returns a conflict error. Sequential tests will always pass. This is the only test that actually validates the select for update. Test idempotency. The same Stripe event ID processed twice. When the second call should return success without reapplying the transition or doubling side effects. And the test most developers forget, completeness. For every state in the machine, verify that every event either has a defined transition or explicitly returns an error. This catches the failure mode where you add a new state but forget to define how it responds to existing events. The new state silently accepts or ignores transitions it should reject. These tests run against the real Supabase database, not mocked. The trigger, the select for update, and the unique constraint are what you're actually testing. Mocks don't exercise those. Make impossible states structurally impossible. Replace Boolean flag combinations with a single status enum. Impossible states become unrepresentable at the schema level, not just conventionally avoided. Guards and database functions with select for update, guard evaluation, and state update are a single indivisible operation. No window between check and write. Select for update for concurrency. One transaction wins, the other blocks and reads the new state. Use for any check, then act on shared mutable state. Unique constraints for idempotency. The database enforces atomically. Even if both applications checks pass, only one insert succeeds. DB, not app logic. Test completeness. For every state, every event must either have a defined transition or explicitly return an error. Missing transitions are silent bugs. For a client, order lifecycle on this platform is enforced at the database level, not by application convention. Invalid transitions are rejected by a trigger regardless of which code attempts them. Concurrent operations are serialized by row-level locks. Duplicate webhook delivery is idempotent by unique constraint. Fleshed out thoughts. I'm building a full stack e-commerce and blog platform with Next.js and Supabase. If you're designing state machines for your own platform, transition tables, concurrency control, database level enforcement, reach out. I'm open to freelance projects and consulting. The full post is linked in the description. Complete transition table, the full transition order status function, and the test suite that exercises every state, transition, and concurrent scenario. Next in this series, database design, the schema behind everything, UUIDs, JSON-B, row-level security, and full text search. I'll see you there.